Okay, Unit 6 progress check. Number 16, no calculator. Gives us a table of values. Our intervals are 1/3 each, so 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. All right, and our R of T, our output in gallons per hour, 11, 8, 5, and 0. So it's decreasing, right? So question number 1 is use the data in the table to approximate R prime of 1/2. Show the computations. So we're looking for how much this is changing, what's the slope at 1/2, and to do this, we want to take the average rate of change from 1/3 to 2/3. So 1/2 is in between here, therefore we're looking for the slope at 1/2, so we need to do the average rate of change from 1/3 to 2/3. So this becomes R of 2/3 minus R of 1/3, all over 2/3 minus 1/3, or negative 9 gallons per hour. So if we're talking about this in a graphical sense, we have this curve. We have two values that we know, and we are looking for the estimate. We're looking to estimate that. Sorry. So we take the average rate of change here, and there is our estimate, which by my drawings is pretty good estimate, but that's our solution. All right, part 2, or part B. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the area under the curve, or the integral 0 to 1 of R of T. So whenever we see a table like this, we need to be considering the fact that we might be doing a left or right or midpoint even Riemann sum, depending on the data. And what we're talking about here is the left-hand Riemann sum. So left-hand Riemann sum would be, I'm using the left-hand values, and I won't be using this value. I also understand that my delta x, in this case my delta t, is 1/3 in every time. So I can represent this two ways. I can do 1/3 times R of 0 plus 1/3 R of 1/3 plus 1/3 R of 2/3, or I can pull it all the way up. And see, this approximation equal sign means it's not exactly right. The area under here, the integral from 0 to 1 is not exactly right. It's an approximation. So I take the 1/3 and I multiply it by the 3 values at those 3 t values. Okay, using the data in the table to evaluate 0 to 1/3 of R prime of t, well, we're looking at calculating the integral of this, and the integral of R prime is R. So this becomes R of t from 1/3 to 0, and we have those values, and this becomes R of 1/3 minus R of 0. All right, and it becomes 8 minus 11, or negative 3. All right, part D. Okay, gives us this summation. This is talking about adding up a bunch of rectangles. That's this Riemann sum. That's what this is saying. And these rectangles have a width of 1/2n. All right, and this is k steps, and this is the Weber starting value, and this is a right-hand Riemann sum with n subintervals. If we got more and more subintervals, this would become a better and better estimate of an area under a curve, or the absolute definite integral. So what we're talking about here in general is a section that is broken up into a bunch of rectangles, and that gives us an estimate using the summation. But if we take n to infinity, we can actually get the definite integral. And that's what we're going to do now. All right. To do that, we need to break this up. This is not as involved. They can make these questions pretty tricky, but this is going to be pretty straightforward. So we're going to break this up into 3 pieces. We're going to evaluate this in 3 pieces. First things first is this piece right here, 1/2n. This is our delta t. This is the end of our dt, dx, so that end of our integral. In this case, just delta t, and it's going to get infinitely small as n goes to infinity. But most importantly, this tells us our interval is 1/2. Anytime we look right here, we're looking right here, this tells us what our interval is. Whatever number divided by n. In this case, it's 1/2 divided by n. In this case, if all this stuff went on over here, and at the end we had this 4 over n, our interval would be 4, because 4 divided by n. In this case, if we had a bunch of stuff over here, and we had at the end 6 over n, our interval would be 6. That's how much that's the length we're measuring. So in this case, it's a little more involved because it looks a little funky with 1/2, but that's just any fraction divided by a number is the denominator multiplied by that number. So this is saying 1/2 divided by n, all right, and it tells us our interval is 1/2. That's the first thing we do every single time we look right there, okay? Secondly, we're going to look at it right here. This is sort of our starting point. It doesn't have to be, you'll see later, but for our purposes it will be. All right, that's where we're going to start on the curve, which means our interval, because it's 1/2, is going to be from 1/4 to 3/4, right, inclusive. Because it's 1/2, we're going to start here at 1/4, and we're going to move 1/2 to 3/4, all right? And lastly, and maybe most confusingly in these functions, is this right here. So imagine, if we're starting at 1/4, and we're taking steps, our delta t, as 1 over 2n, that's the length of our steps, then this is k times the number of steps. So if I have k equals 1, then it's 1 step of 1 over 2n. If k equals 2, then it's 2 steps of 1 over 2n. And all we're doing, when I'm talking about steps, I'm talking about moving, inside of our interval that distance. And that is our right Riemann sum. If this were a left Riemann sum, this would either be starting at 0 or be subtracting 1. But a right Riemann, this would be starting at 0. Or a right Riemann sum means we're starting here, and we're moving here, and we're evaluating right from the very beginning. So if this were a left Riemann sum, this would be k equals 0, or this would be minus 1 over here. More than likely k equals 0. All right? But anyway, this is a right Riemann sum. So remember, we're starting on the left-hand side, and remember how we evaluated it first. We'd move first, and then we use the right-hand value to measure. That's what's going on here. Okay? Now, from here, once we understand this interval part is really important because that gives us our definite integral. See, but we're going to move down here. That gives us our 1/4 to 3/4. Our function is simply r of whatever our t value is, right, dt. And that's it. So really our value is this 1/4 to 3/4. That's the key part. All right. Now, on that note, on your answer keys, you have this written, that the limit can also be written as any definite integral of this format. So imagine our a, in this case our a was 1/4, right? But we could have it be anything as long as the top boundary is 1/2 away from that original value. So we have it as 1/4 raised to 1/4 plus 1/2, or raised to 3/4. This could be anything. This could be any value of a, and when I would have to adjust it is I adjust it in here. So this is a little bit like U substitution, changing boundaries. But don't concern yourself too much with this. I just want to make mention of it so you can understand that's their explanation, okay? We would be better off just not overthinking it, identifying our delta t, which will give us our interval, which will give us our difference, starting from there, and we can then get to our definite integral. Okay? All right. Okay, so a quick example, similar to what we just did. I give you this summation. The function is f, and we have a 5 plus 6k over n, parentheses, 6 over n. So I want you to look right here to begin with, and there's our delta t, so our interval is 6. All right, that's the first thing we need to do, okay? Then secondarily, I want to look at my starting point. This is my x value, or in this case my t value I'm starting at. And these are my distance of my steps times the number of steps, times k. So 6 over n, remember, is my delta t. So that's how big my step is. And then if I'm taking 1 step, it's times 1. If I'm taking 2 steps, it's times 2. And all that's doing is taking me down the interval, k steps of a distance of 6 over n. All right, so that's what that means. All right. Therefore, the answer is, if I were going to take the limit as n goes to infinity, right, of that function above, I didn't realize those last parentheses are excessive. So all of a sudden I take this, and then I plop this limit on it, it becomes this, the integral of f of t dt from 5 to 11. As we mentioned before, we could have this be a to a plus 6 at any distance, 12 to 12, I'm sorry, 12 to 18 or something like that. But let's just stick to the most basic, which is going to be 5 to 11 f of t dt. But remember, we have this summation, and then we plop this limit on it, and it becomes the integral. Very similar to, we have a secant, or the average rate of change formula, the difference quotient, and we plug the limit on that, and it becomes the derivative. So the exact same concept moving on here. Okay? All right, done.